All right, so today we will start proving this theorem. A subspace of R is connected if and only if it is an interval, right? So that's the statement. Okay, suppose, let's do first the easy part. Suppose I is not an interval. Then we have what? What was the definition of interval? Definition of interval was the following. A subset or I of R is an interval if whenever we have 2 points in that set A, B, let's say A is less than B, then all the points between A and B are in I. So if a subset is not an interval, this means that there's a pair of elements in I so that this A and B has an element in between, and that element doesn't belong to I, right? So if I is not interval, then there are elements A, B in I with A less than B, and a third point, let's say C in a real number C with such that C is between A and B, but C is not in I, okay? All right, but you see, if there is something like this, you see we have the following situation. A, B is here. A and B belongs to I, right? So this is belong to I, but this one is not. Well, then we consider the following open sets. Then, okay, let U to be minus infinity C and V to be C plus infinity. Since C is not in I is in subset of R minus C, and R minus C is just U union V. Also, U union V is clearly the empty set, right? Moreover, I is in U, right? U is this part. So let me say U is this part, right? And V is the other part. So A is in U, and B is in V, so that U intersection I is not empty and V intersection I is not empty. Well, this means that U and V is a separation for I, right? So I, which is just U intersection I union V intersection I, is a separation for I. Hence, I is not connected. Okay. So if I is not an interval, then it is not connected. Now let's do the other way around. Now suppose that, assume that I is an interval. So we must show I is connected. Okay. Well, on the contrary, let's assume that I is not connected. Assume on the contrary that I is not connected. And suppose this lies in some open sets UV, where UV open subsets of R with U intersection V is empty and I intersection U is empty and I intersection V is empty. So in other words, U and V, in other words, I equals I intersection U union I intersection V is a separation for V, for I, sorry. Okay. Well, how can we prove that I is connected? I assume the contrary of this statement. Okay, so we assume that it is not connected. So, all right. Now, let, for example, A be a point in I intersection U. Okay. Okay. And let be a point in this, right? Since they are both non-empty, I have this. So A is, assume that one of them is larger than the other one. Assume that without loss of generality, A is less than B. So we have this, okay? Well, so this belongs to U and this belongs to V. Now, what I will do is the following. I'll just start from this point and move towards B up to the point where the point is no longer in U. Okay, so let's do this. Let C be the supremum of the following: supremum of A comma X, supremum of X, sorry, so that AX belongs to U. Okay, so I look at points so that the interval AX belongs to U. Okay, and I choose C to be the supremum of such x's. So Okay. Now, first of all, since B is in V, right? Since B is V, therefore it is not in U. So this C we must have, we have C is less than B, right? Okay. Ya küçük eşit diyeyim. Okay. Indeed, in fact, if okay. Ya aslında buna gerek bile yok. Var mı gerek? Neyse tamam. Yani sonuçta doğru bir ifade. Okay. We have two cases. Case 1. Well, C is in, of course, I, right? Because since C is in B, right? Because it is larger than A less than B, C is in I, because I is an interval, and therefore, whenever you have 2 points in that set, anything between them belongs to that set. So C is in I. Well, there are two cases. C might be in U. Well, if C is in U, then of course U is an open set. Open set. Since U is open, there is some R positive, so that C minus R, C plus R lies in U. So in other words, if this point belongs to U, then there is some neighborhood like this, and this whole thing should belong to U. But then well, I know that A and anything less than C. Let's choose a point here, Y, which is less than C but larger than C minus R. Then AY belongs to I. But this interval also belongs to U. Yeah, I mean this belongs to U. Why is that? Because C is the supremum of all x's such that AX belongs to U. So if I choose something less than the supremum, then the interval from A to that point, which is Y, this point, okay, this point, that belongs to U. And C minus R, C plus R belongs to U. So this whole interval belongs to U. Therefore, the union of these two intervals, which is just A C plus R, is belongs to U. So let me do it this way. Now C plus no, cy, which is c minus r minus 2. So what I'm doing is this. Okay. C is here. R is like this. Let's say R. And this point is c minus r minus 2. So I call it y. Okay. This y, by the choice, this okay. Şöyle diyeyim. A y belongs to u, where y is c minus r over 2. But this thing also c minus r, c plus r belongs to u, and thus a comma, so up to y, and then from y up to c plus r, or c plus, yeah, r over 2, the closed interval. This belongs to u. So this means that what? Hence, uh, supremum of uh, you know, supremum of this axis such that ax belongs to u, since this is less than okay. This supremum is greater than c plus r over 2 because it contains this point. Okay. And this is a contradiction. A contradiction. If what, unless, okay, c yani ne zaman şey olabilir? Şu interval tamamen şeyin dışındaysa, i'nın dışında kalırsa bu kısım şey olur. Öbür türlü bu contradiction. Okay. Diğer durum ne? Case 2. C is not in U. Well, then, of course, C is in V. But V is also an open set. Since V is also open, there is some R positive, so that C minus R, C plus R belongs to V. But this time we have this A. Okay. A is here, B is here, and C is here. C minus R, C plus R, and this whole thing belongs to V. So this point, let's say C minus R over 2 belongs to V. So C minus R over 2 is in V, and thus C minus R over 2 is not in U. But we know that, however, we know that uh, A, anything less than C, so C minus R over 2 is in U by the choice of C. And that's a contradiction because here I say it's not in U, but here we say that it is in U, right? Remember, C is the supremum of all the x's, so that A comma X belongs to U. Therefore, if I choose something less than C, then interval A comma that point should belong to U. Okay. So anything less than C belongs to U, but if C is belong to V, then of course an interval like this belongs to V, and that gives me the contradiction that this point C minus R over 2 belongs to both U and V. This is a contradiction. Hence niye geldi bu contradiction'lar? Burada şeyi kabul ettiğimiz için. Assume on the contrary dedik. A is not connected. Bir C sayısı bulduk. İki durum var. C ya U'ya ait ya da ait değil. Ama her iki durumda başımız derde girdi. O zaman demek ki assumption'ımız yanlışmış. Hence I must be connected. So any interval is connected then. Okay. Yeah. Yeah, sure. Here I am using, you see, I used open intervals as my open sets, basis elements of open sets. So we are using, standard topology. Sure. You can put R different topologies and R becomes anything you want, okay? You can put discrete topology, then the only connected sets becomes singletons. Okay, because each singleton is an open set. So only one point sets would be connected. So here maybe I should emphasize that our standard is connected. Well, intervals are always defined. It doesn't depend on the choice of the topology. But whether an interval is connected or not depends on the topology. And an open interval may not be an open subset in a topology other than the standard one. Okay? So open intervals are open in the standard topology. If you choose a different topology, an open interval may not be an open subset anymore. You may call anything you want an open set, okay? As long as they satisfy the three axioms of topology. What are they? Empty set and the whole space should be declared open. And any union of the open sets you declare will be open, and finite intersections of the open sets will be open. But then it is up to you how to define your open sets. Okay, you may define them any way you like, as long as they satisfy that three conditions. Okay. Well, of course, this means what? Any interval is connected, so R, of course, is an interval, right? Or this interval, this interval, this one, and so on, are all connected subsets. Of course, since R is connected, R cross R is connected. And we will see that actually infinite product is also connected. We will do that one also. But before we pass to that, we have another result, which is something we are familiar from freshman. Yeah. Yeah. You mean other products? I am not sure. I don't remember actually. But it might change. I am not sure. Once we see the proof for this one, I may say something, but at the moment I don't remember. So you mean, for example, this is connected, but what about this, right? Yeah, okay. Yeah, I don't know. Probably not, but I mean, probably it is connected, but I am not sure. So let's just wait. So you see, I don't recall such facts easily because I don't see them much around. They're kind of weird objects unless you study them. Okay, so what's the intermediate value theorem? Let f from x into R standard be a continuous map. Okay, where x is a connected space. Okay. The conclusion is this: if, let's say, A and B are in R standard, are in the image of F, and C is a point in between, then there is some then C is also in the image of F. So here is the proof. Let me first draw a picture. This is a symbolic picture because we don't know what x is. Okay, x is just any space. I draw as if it is the real line, but it may not be. The thing we know about x is that it is connected, and the points A and B are in the image of F. It means the graph is something like this, and there is some, let's say, x1 here, which maps to A, and there is some x2 here, which maps to B. What this theorem tells us is the following. If you choose an intermediate value between A and B, then you will find some x naught here, so that f of x naught will be equal to c. Okay, so any intermediate value is in the image of f. Okay, so that's the statement. All right, y equals f of x. Now let's see the proof in detail. So let x1 and x2 be points in X with f of x1 is equal to A and f of x2 is equal to B. Okay. Right. Since X is connected, and f is continuous, f of x is a connected subset of R standard. But we have just seen that connected subsets of R standard are just intervals. Hence, f of x is equal to an interval, Well, A and B belongs to this interval. Clearly, A and B belongs to this interval. And C is between them, since C is in between A and B, and I is an interval, and I is an interval. C also belongs to this interval. But what is this I? I is the image of F. So there is some other point, let's say x0 in X with f of x0 is equal to C. Okay, let's prove the result. Okay. All right. There is another notion of connectedness, so-called path connectedness. Let me talk about that. Given points x and y of a space X in X from X to Y, continuous map F from AB into X with f of A equals X and f of B equals Y. Okay. If we can find a path between any 2 points of a space, then we say that that space is path connected, because whenever you give me 2 points, I can find a path joining them. Okay, so I can find a path joining these 2 points. That is just a continuous map. Okay. All right. So let me finish the definition. A space X is called path connected if any 2 points of X is connected by a path. Okay. All right. Okay. Some maybe examples. Okay. Any convex subset X of Rn is path connected. Why is that? Convex means the following. Recall that a subset X of Rn is called convex if what happens? If whenever x, y are in X, then the line segment, which line segment? This one. T maps to 1 minus t times x plus ty. T is from 0 to 1. Also belongs to X. So a convex set is something like this. Okay. Whenever you have 2 points, the line segment joining these 2 points, okay, a point like this. So this is 1 minus t times x plus t times y. When t is equal to 0, you are at this point. When t is equal to 1, you are at this point. And when t is between 0 and 1, you are just on the line segment joining x to y. So if a set contains all the line segments joining 2 points of any 2 points of this set, that set is called convex. And we claim that a convex set is path connected. Why is that? Because, well, you see already a path, right? Note that f of t just 1 minus t times x plus t times y is already a continuous path with f of 0 equals x and f of 1 equals y. So I have already a path joining x to y. Hence, x is path connected. All right. One more example. Balls, Euclidean balls. Okay. Any Euclidean ball. So B XR. What is this? The set of all points in Rn, so that the Euclidean distance x to y is less than or equal to R is path connected. Right? A ball is, of course, a ball is convex, right? Well, okay. Whenever you have 2 points like this, then they say this is the center, this is the radius. Whenever you have 2 points, then the line segment joining these two belongs to ball. Why is that? Well, I guess you may just look at the difference between distance from yeah. Okay, so okay, my picture and this notation is somehow okay. So let me say this is O. Ya da şöyle diyeyim. Buna neyse x0 R diyeyim. X0 da x olsun. Şurası x0. Okay. Bunu size exercise bırakayım. Bu gayet kolay bir şey. This is an easy fact. What you need to show is that distance, I mean, if you choose, let me say this point is, say, x1 and x2, 2 points, and choose a point on this line segment. So y is a point given with this coordinate. So x1 and t times x2. You have to just look at the difference between x0, y and x0. Okay. Well, what is this? Y is just, okay, 1 minus t y plus t times y minus, no, I mean this, sorry. Y is 1 minus t times x1 plus t times x2. Yes. And x0 is 1 minus t times x0 plus or minus t times x0. Okay. Well, this is just 1 minus t times x1 minus x0 plus t times x2 minus x0. Yes. And you see, I have a vector, another vector. Norm of the sum is less than the sum of the norms, right? By the triangle inequality. However, norm of a vector multiplied with a scalar is equal to that scalar times the norm of the vector. So this is just the absolute value of the scalar times the norm plus absolute value of the scalar times the norm. But t is something between 0 and 1, so 1 minus t is also non-negative. Therefore, this absolute value is just the real number 1 minus t, and this is x1 minus x0. plus t times x2 minus x0. However, both x1 and x2 are in this ball. Therefore, this thing is less than r, or maybe equal to r. It might be on the boundary. I include equality. And this thing, again, is less than or equal to r. So this thing in total is less than 1 minus t times r plus t times r. But that adds up to 1. Therefore, hence, the distance from y to x0 is less than 1. So this means that y is in the ball with center x0 and radius 1. Okay. Uh, hmm. Yeah. Sorry. Tamam, sağ ol. And here I have to be a little bit careful. Either I will take closed ball or open ball. Here I take open ball, but here I wrote closed ball. So either let me make it open ball. Okay. So this will be like this. Yeah. All right. Of course, if open ball is connected, then its closure is also connected, right? Any set which is the closure of a connected set is closed, is connected also. Therefore, closed ball is also connected. This may not be true for all metric spaces, because in some metric spaces, right, closure of the open ball may not be the closed ball. Never mind. Okay. All right. What else? Okay. We will see in the next hour that not all the spaces are okay. Did I tell you that? No, I didn't tell you that one yet, right? Did you say path connected spaces are connected? No, I didn't. Okay, so here is a proposition. Sorry, proposition. Any path connected space is connected. And proof. Okay. We will say suppose it is not. Okay. Let X be path connected, but not connected. Well, then of course we have the following. Let UV be a separation for X. Choose points. X is in U and Y is in V. Since our space is path connected, since X is path connected, there is a path F from AB into X, so that f of a is equal to x and f of b is equal to y. This will give us a contradiction, but let me just do it in the second hour.